Hi everyone, this is a video where I want to address some of the things that came up in midterm 3. We've talked about this a little bit in class. Ideally, I'd be spending something like 20 or 30 minutes in class going over some of the things that happened, but we haven't really had time on Monday or Tuesday before the break, and I do think that we're going to need the full hour to discuss content for the upcoming days, and I really don't want to rush the content to try to squeeze in this. Nevertheless, I also want you to have this information, and I want to tell you some things about the exam so that you don't make the same mistakes in an upcoming test. So I don't know exactly how much this is relevant for midterm 4, but it's certainly these things came up in midterm 2, and they will come up again on the final. So I just want to make sure that I address as many of the issues as possible. And I will say this: I'm not trying to say any of these things to make you feel bad. Definitely not. I just want to point out the kind of common mistakes that were made. I think that's important to do because I don't want you to make those same mistakes for an upcoming exam. So here's, I don't know with what quality you can see the questions on YouTube here, but question 1 was quite routine. Most people actually did just fine on this. Some people kind of skipped the question altogether, which was a little weird for me because for the angle between the two vectors presented, you would need to use the cosine angle formula, right? So theta is supposed to be the angle, right? And then cosine of that angle is supposed to be u dot v all over the magnitude of u times the magnitude of v. Okay, so that was a question that was asked in the practice exam, and then in the actual exam you just actually had to use this formula. Once you plug in for all these things, you're going to have to say that that theta is going to be cosine inverse of all of this stuff here. Part B, I think it was fairly routine for people again. Here you had to take two vectors and multiply each of them by a scalar, then add. This question I actually modeled off of a quiz. In a quiz a while back, I forget which one, you actually had to do something like this and then afterwards find the magnitude of the vector. So anyway, I think question 1 was routine, and most people did actually quite well on that. Question 2 was about solving a triangle and then finding the area. In the practice exam, you saw SSA, that was the ambiguous case, and the solve the triangles question came first, and then finding the area came second. I intentionally flipped the two here because I didn't want people trying to work through some kind of ambiguous case that may or may not have come up. Because there isn't one. So when you have this side-side-side case, there is no ambiguous case unless you create one yourself. So there should be no ambiguous case. Nope, no ambiguous case. And with side-side-side, it's helpful to use Heron's formula. So that was let S equal the length of the 3 sides, but then divided by 2, and then the area is supposed to be square root of s times s minus a times s minus b times s minus c. And the point of putting this area thing here first was if you just plug in these numbers, so in this case 5 plus 7 plus 10 all divided by 2, so what is that, 22 over 2 or just 11? Then I wanted this to be a very, very, very short process. The area is going to be square root of this quantity, 11 times 11 minus 5 times 11 minus 7 times 11 minus 10. And you could leave your final answer like that. Now, a lot of people actually ended up switching the two. Maybe didn't read the questions as they were presented, but I did try to put them in this order to try to get you to think about using Heron's formula. A lot of you actually ended up doing something like this, using a different area formula, such as 1/2 AB sine of gamma, which is totally fine. If you did that and you used the correct angle, which you found from this part, full credit for that, totally. But I just think that this is a lot more work, and this formula is very succinct and good to use in the side case. As far as solving the triangles go, a lot of people tried using law of sines only. If you tried that, you didn't receive any points. What you do need to do is, when you have the side case, you have to use law of cosines. And the thing to do is, you can use law of cosines for each of the three angles. And that's fine, but if you use the law of cosines and then want to use the law of sines, so if you want to use law of cosines followed by law of sines, then law of sines, then you have to find the biggest angle first. Then you must find biggest angle first. Right? So in this case, since C is biggest of A, B, and C, then you must find gamma first. Okay, that's I think all I'll say about that one. Here, question 3, this is perhaps the only thing that I don't think was actually modeled off something in the practice exam, which is, you know, maybe that's a little bit harder, but we actually did a number of questions that looked like this in class when we talked about inverse trig functions. This particular question was actually one of the assigned textbook exercises. It was page 493. Question number 15, part A. And the point was, we did kind of a number of questions that look like this. And for all of these, I tried to say this several times, but when you have one trig function and then another trig function, so different trig functions, one with the inverse, one without, you're going to have to take the inside thing, you know, work your way from inside out, and do something like set up theta is equal to sine inverse of 2/3. And I know I've been trying to emphasize this a little bit more as class has gone on, but you should actually set up a variable like this to really organize what you're doing, because once you do this, once you say that theta is equal to sine inverse of 2/3, then you can take the original question, right? The original question was to find cotangent of sine inverse of 2/3, and then you can just reword the question. So this is it's really the same question, it's just said in different terminology. So since it's going to be the same question, it'll have the same answer. Then, because the thing in parentheses is what you call theta, then now what you're trying to do is find cotangent of theta, right? So I'm trying to I think maybe this was perhaps the most challenging thing on the test. It was the thing that most people skipped, and I was a little shocked to see that. But I do want you to think about these problems, and really all of mathematics, kind of less as a recipe, but to think, okay, well, what do I have? Well, what do I want to get? Or here's a question, how do I reword it? If I reword it like this, then I have this new variable. Well, how do I use this information to get what I want, right? To always try to phrase things in the form of, what do I have and how do I get what I want next? Okay, part B, this was the reverse of a question that was on the practice exam. So in the practice test, there was something like this, r times cosine of theta plus I sine theta. I believe it was question 3, part C, and then you had to convert something like this into the form a plus bi. And there were 2 solutions shown. And I put this on here on the practice exam because we hadn't actually seen much of this kind of problem in class. Though it should have been doable anyway. What we actually saw a lot of in class was the very question like the one that was here. So in class we actually saw things like taking a plus bi, something of that form, and converting this into something of the form, into this trig form, r cosine theta plus I sine theta. Okay, so we had done that several times, and the thing is, you could think of this using some kind of formulas, and I know we did write something like this down in class as well, that the r you can get is going to be root a squared plus b squared, and that theta is going to be found as tangent inverse of b over a. And this will depend actually, so there are some details here about what quadrant you're in. So we did maybe less of writing down formulas like this, but really trying to do things like draw a picture of the point, right? So if that's where a plus bi is, maybe because a and b are positive, like in this example in the first quadrant, then you can draw a picture of the angle theta and just use trigonometry to try to answer the question. So I'm trying to, I don't think this was really a trick question. We actually saw a lot of routine questions like this. But if you get stuck, the thing to do is to draw a picture and to try to relate things back to some of the trig we learned earlier in the semester. This question, I hope you've looked at the solution for it on the website. So the thing is, I also picked this intentionally because of what I put in the practice exam, hoping that this would help you out. So there were two questions on the practice, and both of the identities to verify required formulas in section 7.4. So that was the section on double and half angles. So this problem did too, and that's why I put two questions which were considerably longer than the solution for this one is if you actually look at the keys. That's why I put those two problems on the practice exam, which were both longer, and this question, which was considerably shorter. So a lot of things that people did was to sort of try to mimic something I think that was in the practice exam. And I mean, there are some sort of good ideas there, but I think some people were maybe over-engineering this. So a lot of people actually wrote something like this, and I was really shocked by this. So saw the -2 sine squared theta there, and tried to overthink, I think, or to try to make this mimic the practice exam too much. And actually, a lot of people replace this, sort of one line down, with something like this. Negative sine squared theta plus sine squared theta. So people wrote that. Or what I really mean is people, nobody really wrote this, but what people did was they took the right side, which was 4 sine theta cosine theta, times 1 minus 2 sine squared theta, and then rewrote this as something like 4 sine theta cosine theta times 1, and then this right here, right, this minus 2 sine squared theta was replaced with minus sine squared theta plus sine squared theta. And I see why people try to do something like this. It's because then you stare at that thing and then you see cosine squared theta. But the problem is this right here was street to begin with, right? So you can't do this because check this out, right? On the right side over here, you actually have a positive sine squared theta and a negative sine squared theta. Those two things cancel each other out. You actually have 0. And so -2 sine squared theta, unfortunately, is not equal to 0 most of the time. All right, so that's one thing that ended up happening. Another thing that people did was people seemed to know and use quite well. So that was one type of issue that came up. But another thing that people ended up doing quite a lot was to take 1 minus 2 sine squared theta and to replace that, the next line down, with 2 cosine squared theta. And those are not equal. I think the reason people did this is because 1 minus sine squared theta is indeed cosine squared theta. So often you'll see 1 minus sine squared theta in a trig identity. We've done things like this in class, and that gets replaced with cosine squared theta, right? And that's okay because you can take this line and add sine squared theta to both sides and get that usual Pythagorean identity. But something happened here. I think what happened was people wrote something like this because it's reminiscent of that. But that doesn't quite work. And what I encourage you to do if you're unconvinced of that is actually take this thing. Let's do this here. Is actually, well, let me have you think about it, because I encourage you to take this here. Start with this and then try to develop this out of it. So start with this and, do things like add the same thing to both sides, or subtract the same thing on both sides, or multiply both sides by 2 perhaps, and from this try to get that, and you won't be able to get it. A number of other people tried this, so let me get another sheet of paper. All right, so in this same trig identity one, people ended up doing a lot of things like sine of 4 theta, for instance, right? This is the thing that was on the left side, would write this as sine of 2 theta plus 2 theta. Now that's okay. What doesn't work is when people write this as sine of 2 theta plus sine of 2 theta. Okay. Here, what's going on is people are using that sine is additive, which it isn't. But then from here, what a lot of people did was they actually looked at the formula on the formula sheet. That was sine of u plus v. So that's on the formula sheet for the exam, for midterm 3 anyway. It looks different than the one for midterm 4. But people use that formula, and that's correct. I mean, that's totally fine to use. So using this formula, you'd get sine of 2 theta times cosine of 2 theta, then finally plus cosine of 2 theta times sine of 2 theta. And all you do is when you use the formula that's on the formula sheet, both u and v are 2 theta. Now when you actually do this, you end up getting 2 copies of the same thing, right? The same term is listed twice. This is really 2 sine 2 theta cosine 2 theta. And the thing is, there's nothing wrong with doing this process of taking sine of 4 theta and then getting this. There's nothing wrong with that, because these are indeed equal, okay? So that's good, but the thing is, this is sort of a waste of time, because the thing to really do is to use this formula down here. Probably too hard to see on the video, but this is sine 2u is equal to 2 sine u cosine u, right? So what you want to do is actually use this formula, but then replace each u with 2 theta. Okay, if you do that, then you have sine 2 times 2 theta. Maybe you can put a set of parentheses there if you'd like. Is equal to 2 sine u is 2 theta. Cosine of u is also 2 theta here. Okay, then this is really sine of 4 theta is equal to 2 sine 2 theta cosine 2 theta. And so the point is this: even though it's not wrong to use this, the point of this sine angle addition formula is it's really most useful to use when you have 2 different angles that you're adding together. When you have the same angle twice, you really end up just rederiving this formula. So it's just a lot faster to use this formula. People did other things like this too. For instance, back in the question, there's this 1 minus 2 sine squared theta, and people did all kinds of actual work that was correct, but lines and lines and lines of work to actually get that 1 minus 2 sine squared theta is in fact cosine of 2 theta, but that's actually a line right here in the formula sheet, right? This line that says cosine 2u is equal to 1 minus 2 sine squared u. So the thing is, it's right there. It's the right side of this formula, and then this has to be converted, you know, going from right to left, into cosine 2 theta. So again, I'm pointing this stuff out because a lot of people wasted a lot of time even doing correct work. But time is not something you want to waste, especially when as a test writer and designer, I'm trying to write things, you know, hoping that you're going to use the formula sheet. So not out of anger, but out of some amount of shock, I thought, well, I need to get US students to look at the formula sheet more, because it doesn't really help if I provide the formula sheet if you don't use it. Now, as you know, I am giving you a formula sheet for midterm 4 and the final. That's posted. It looks a little different than the one that you've been given for midterm 3. In fact, it has more information. And the thing is, a lot of people tried to use some of the formulas, and even when using the formulas correctly, did not use the ones that would help the process the fastest. I guess the way to say this is that people were not efficient even when they were correct. And I guess my view of that is this, is that though I provide a formula sheet, if you don't use it, then that's just not helpful, right? I mean, you have to know not necessarily every time when to use which formula, but you have to have all these formulas in your mind. So the point of providing the formulas on the formula sheet, in my opinion, is that there are formulas like these ones over here, which are so similar, they're just off by pluses and minus signs. I think that's a lot of work and stress to try to memorize. So I don't want you to memorize that, which is why you have a sheet like this. On the other hand, you know, when you start a trig identity like this, I really encourage you to be thinking now, where have I, as you work even line by line, you know, as you move down into the next steps, is to think, now where have I seen anything that looks even something like this? And I'm not saying you have to memorize that 1 minus 2 sine squared theta is cosine 2 theta, right? That's why you have the sheet. But you do have to have that thought, you know, at least 80% of the time that you do one of these kinds of problems, to think, now I've seen something that looks like that. And then you have to go to the formula sheet and go, I think it was some kind of double angle, but was it sine of 2 theta? Was it cosine of 2 theta? That's the kind of thought that I want you to have. And then you come to the sheet just to simply verify that, right? Because if you don't use the sheet in this way, and if you're not familiar with what's on here, not to the point of memorization perfectly, but to the, oh yeah, there was something that looked like that, then it's like you're not using the sheet at all, in a sense. And if you don't, I mean, I will provide you the sheet, but if you don't use the sheet, you might as well burn it right before you start the next test. And again, I'm not saying this to be overly sarcastic. I'm just trying to put it in a bit of perspective. I want you to look over these formulas and be familiar with them, which is exactly why I provided that list of questions of, you know, there's a guarantee that a certain type of question is going to show up on midterm 4, and it's my attempt to try to get you to become as familiar as possible with these. Midterm 4 will not have a verify the trig identity that looks like this. The final will have something like this, and so this is to try to get you to, you know, to warm up and become familiar with these so that you're ready for the final. So I hope, I know maybe it is a little stressful to be told that midterm 4 has a certain type of question. I do hope that that information, you use it in your favor, and please understand that I am doing that because I want you to be as prepared as possible when you see an identity. You will need to use formulas on the formula sheet, and I'm just trying to get you familiar with them. Question 5, there were a number of sort of things that came up. People did things like took the sine of 6x minus 4x, and people actually started right away doing things like setting sine of 6x equal to 0 and sine of 4x equal to 0. So you can't do that. Can't do that, right? Another thing that people did was subtract sine of 4x on both sides. That's okay. So that is what you in fact need to do. Sine of 6x minus sine of 4x equals 0. And then people here actually did the same thing of taking each of these individual terms, and that's the key word, they are terms, and setting them equal to 0. Now you can't do that, right? So you do need a 0 on one side, but you have to have stuff multiplied together that's set equal to 0. But here you have stuff subtracted from each other. So the thing is, you can't take individual terms and set them equal to 0. A thing that some people did was actually then took this line and then wrote sine of 2x equals 0, doing some kind of subtraction of 6x minus 4x to get 2x, I presume. But you can't do that. Okay, that's using the idea that sine is additive, right? That 6x then plus maybe the negative 4x would give you 2x, right? I was shocked at really the number of people that did a process like this, especially because we actually had a quiz. I forget which quiz it was, but it was a one where some formulas were actually provided, and you have to use a sum to product formula here. So I think the thing to do is this. I want to point out, you have to keep in mind that there's really a difference between sine of u plus v, which is on the formula sheet somewhere, and sine of u plus sine of v, which is also on the formula sheet somewhere, right? And just really take, so this is the left side of some formula, that's the left side of some formula as well, and you have to take the expression that you have and analyze which of these it looks like. Oh, I guess it's the one with the minus signs, but same idea, right? So here you have a sine of u minus sine of v, so you got to go to the formula sheet. I guess on the formula sheet it's called sine of a minus sine of b, right down here. But you have to use a formula like that in this situation, right? So in neither of these cases, so this does not equal that, and this does not equal that. And that's really, I guess, one of the key points, is that people, we talked about this for the last test too, so the same problems are still coming up, but don't say that sine of adding two things together is the same thing as adding together the sine of the two things. And the same really goes for subtraction. So since what you have looks something like this, although with a minus sign. Go to the sheet, and the point is that once you convert the other side, you have products of stuff. Okay. And then that's good, right? So if you replace this expression here with a product, then you have stuff multiplied together set equal to 0. Then you can set each of the factors equal to 0, which is what you want to do. Last thing is this last question here. This did, again, try to mimic, so both parts here also try to mimic something on the practice exam. Here people sort of, I guess, tried to get this, people did things like this to actually say something like 2 to the 2 times the quantity 1 plus cosine squared x is equal to 4 cosine x. And the thing is, look at what happened going from one line to the next. The only change in here was to change that 2 to a 2 instead to a 2 squared. Right? So this is not adding something to both sides. This is not subtracting something on both sides. This is simply changing a 2 in the original problem to a 2 squared. Right? So 2 became a 4. Right? So that's not going to work. And I understand why people did that. It sort of mimics something on the practice exam, but that was sort of the wrong mimic. So the thing that I wanted people to do was to say, well, here, leave the left side alone. 2 to the 1 plus cosine squared x is equal to. But then there's a 4 on the right side. Now 4 is 2 squared, right? So see that's different. So here, what people did was to change the 2 into a 2 squared, and 2 is not equal to 2 squared. Sorry, let me finish writing this. Times to the cosine of x power. So here, what happens is the 4 gets changed to 2 to the 2, and those are the same, right? 4 is equal to 2 squared, and then there's a cosine x up in the exponent. So, look, on some level, I understand the mimicking that occurred here, but maybe instead of copying something, what I want you to do is kind of go over the practice exam again and go and ask yourself, well, why did he even write the kind of thing that he did? And maybe the sides are swapped from the practice exam, but that wasn't even I guess that wasn't a thing I was considering that might happen. But the key thing is, you can't, if you're not going to add something to both sides or subtract something on both sides, multiply something on both sides or something like that, the thing to do is you have to change an expression on one side or the other into something that's equal. And the point is 2 is not equal to 2 squared, but 4 on the right side is equal to 2 to the second. From this, you'll get 1 plus cosine squared x is equal to cosine x. Now people did sort of the same kind of things as happened in the previous question. People did things like set 1 plus cosine squared x equal to 0 and cosine x equal to 0. Can't do that. You got to subtract this on both sides. And when you subtract cosine squared x, when you subtract cosine x on both sides, you're left with cosine squared x minus cosine x plus 1. Whoops, I made a mistake here now. This 2 should distribute up here. You get 2 cosine x. So this will be cosine squared x minus 2 cosine x plus 1 is equal to 0. Sorry about that. So even when you get down to a line like this, people tried doing things like taking the first 2 terms of the 3 and factoring out cosine of x. But the point is, if you do that, you still have a plus 1. So you have to take the entire thing and factor somehow. And one way to do this would be to, for instance, set up z is equal to cosine of x. So what I want you to do is look at this, and we actually had a lot of web work questions over several different assignments that addressed questions that look just like this, right? The point is, if you make that substitution, this question is now z squared minus 2z plus 1 is equal to 0. And now this is a quadratic. So you could use quadratic formula, or in this case it's easy to factor. The point is this, is that at some point you're going to have to bring back some of the algebra from before, right? Not every question that appears to be about trigonometry is going to be about trigonometry right away. I will make one other comment at this point. So it really affected both of these kinds of questions. The same kind of thing actually happened in both of the previous, in midterm 1 and midterm 2. But really here I was kind of shocked to see this, that people had questions that look like this: sine of x is equal to 0, cosine of x is equal to 0, and would solve both of these the same way. So people would do things like say that x is equal to k pi. Now one of these is true, right? For sine of x, the solutions are going to be of the form x is equal to k pi. That's not the only way to say this, right? So the one that's wrong here is this one is not right. A different way to say this would be x is equal to pi plus k pi. This here is actually the same as 0 plus k pi. Another way to say this is x is equal to 2 pi plus k pi. I mean, the point is you have to start at either 0 or not write it at all since it's 0 plus, but either start at 0 radians, pi radians, or 2 pi radians, and say, okay, those are one of the angles where sine takes on the value of 0. And then where are all the next times? The next angle is always found by adding just another multiple of pi. So, I mean, go back to thinking of the unit circle here, because for cosine, here you need to have pi over 2 plus k pi, right? Another thing, so, and people did things like actually, I don't know if it was out of nervousness or being rusty with the unit circle, but people did, you know, as was pointed out, people took cosine x equals 0 and wrote something like this one and said that's for sine, and some people actually took something like sine of x equals 0 and wrote this instead. So don't switch those two around. I mean, remember that cosine is the x-coordinate and that sine is the y-coordinate. Another kind of issue that came up was people did things like this. So cosine of 2x is equal to 0. Did the kind of substitution like alpha is equal to 2x. Okay, that's good. And then people did things like write, you know, alpha is equal to pi over 2. Right? This is simply because with the substitution you have cosine of alpha is equal to 0. Now alpha is equal to pi over 2 is indeed one angle where cosine is 0, but just writing this alone is only a partial answer, right? And the correct full answer in this case is to say that alpha is equal to pi over 2 plus k pi. Now why am I pointing this out is because what a lot of people actually did was from here to do something like say here using the partial answer, okay, since alpha is 2x is equal to pi over 2, okay, good, then x is equal to pi over 4, great. And then from here people did things like say, oh, so then the final answer that we're going to need is going to be that pi over 4 from previously, but because of what happens, you know, every half circle we get a new angle, we should add a k pi here, right? And this turns out not to be quite correct. It's almost the right idea, but the point is you start with this partial answer and then something goes wrong here. So what should be done is this. Say that since alpha, here's a full set of solutions. Alpha is equal to pi over 2 plus k pi. Now that alpha can be 2x, so then you have 2x is equal to pi over 2 plus k pi. Then what happens in solving for x is that you divide by 2 on both sides. So then x is equal to pi over 2 plus k pi all over 2. Now the point is that this is a decent final answer, and these two are different. Or to really make it clear, a different way to write a final answer would be to take that divide by 2 and put that into both of these terms. Then this is pi over 4 plus k pi over 2. And now maybe it's a little bit easier to see that these are different, right? Because you still have this pi over 4, but then you have plus k pi over here and k pi over 2 on this side. So the point is that one of these two things are good final answers, and the point is that this is really something else, right? So you don't want to stick on this k pi later because of what happens with this division of 2, right? So you need to make sure that this dividing by 2 affects the entire set of answers here instead of sort of going back at the end and saying, oh, right, I need to add a k pi here. If I can just point out one other set of sort of things that people do in this kind of question is in something like cosine of 2x equals 0, people have done things like set up alpha is equal to 2x, okay, good, and say we're going to solve the question cosine of alpha is equal to 0, and say, aha, so from this the kind of solutions are, even saying this correctly, people say things like alpha is equal to pi over 2 plus k pi, and then start saying things like this, that cosine of 2x is equal to pi over 2 plus k pi. And the thing to keep in mind, so this is not quite right. you want to make sure that you keep apart what things are angles. So here, that's an angle, alpha's an angle. Since alpha's an angle, this entire thing is an angle. And you want to separate the idea of what's an angle from what is a ratio, right? So trig, the output of a trig function is supposed to be a ratio. So 0 is supposed to be some ratio, or the x coordinate on the unit circle. And over here what happened is this angle, since alpha is an angle, this is an angle, and this angle ends up over on the side that describes the ratio. So somehow there's a lot of things going on that are sort of mixing together and saying something like this. In a sense, this is quite grammatically incorrect. And from here, it's going to be hard to recover an answer. People have done this on midterm 3 and on midterm 2, and then in the next line did something like this, which ends up being correct, but somehow in a sense by being lucky, right? And all that happened in going from this line to this line is just conveniently ignoring the cosine. So something really weird is happening in doing something like this, is that some weird thinking is going on here, and then additional weird thinking gets you back on track. So don't do something like that. Go back to this idea here to get a full list of solutions. There's one final thing I'd like to point out, which is people also looked at a question like this and did a substitution like beta is equal to x, and then said, all right, let's solve cosine of beta is equal to 0, got beta is equal to pi over 2 plus k pi, which is all correct, but the point is there's no need to do a substitution in this case. Right? So when you look at the old problem here, when you have something like cosine of 2x, it makes sense to substitute alpha is equal to 2x, because this substitution takes this harder looking problem and takes it down to a sort of a more basic or primitive problem. But over here, there's no point in doing that substitution. So several people did substitutions like this on the test, and all that really says is that first of all, on some level you're wasting time, but I want you to go back and think about why doing a substitution like this makes sense in the first place. The point of doing this is it makes it convenient. It makes it so that this kind of question instead has an easy. We've reworded this question into something that's easier. All right, if you made it to the end of this video, congratulations. I did not know that it was going to be 37 minutes long. If you have watched to the end, good for you. I do hope that some of the ideas that have been presented here, if you've made some of these mistakes, again, it's not to make you feel bad. I just want to point out the common things that are going on, and here's to hoping that a lot of you have watched this video all the way through, and that this will result in very, very high scores for the upcoming midterm and the final. All right, thanks for listening.